Hey guys, I just wanted to do a quick recap on binary to decimal as well as decimal to binary. We're going to just cover things about binary since most of you should be familiar with decimal already. So binary is base 2, meaning that it consists of only 0 and 1. And keep in mind, too, these placeholders. So if you're starting, or everything from the left of the decimal, it's going to start from 2 to the 0, and it's going to keep increasing the farther left you go. And to the right of the decimal, starting in the 10th place, it's essentially going to be decreasing, but the way I have it written here, maybe it might not be obvious to everybody, but 2 to the negative 1 is the same as 1 over 2 to the 1, and then 2 to the negative 2 is 1 over 2 to the 2. And as you keep going farther right, everything's going to get smaller and smaller. So there's a few definitions that you should keep in mind. I mentioned briefly in one of the videos what a bit was, and a bit is pretty much the smallest unit of storage, and it's pretty much just, it's a 0 or a 1. That's all it is. And a term that I didn't cover, but if you're doing anything with computers or taking a circuit class or anything like that, you're probably going to come across the term byte. And 1 byte is 8 bits. It's just 1 byte is just a group of 8 bits. So for example, we can have something like and this would be 1 byte. Okay, so what's the usefulness of binary? And when I say usefulness, I just mean pretty much like what applications does it have? Well, one of the ones that a lot of people are probably familiar with is computers. The reason why it's useful in computers is because the 0 and the 1 can represent different states within, like the circuits and stuff like that. So 0 will be an active low, or it's also known as being off, and 1 is an active high, which is also known as being on. You could think of this as a light switch that's connected to, or I'm sorry, the light switch just because, in one position, when you turn it on, it'll turn on the light, and then when you turn it off, it'll turn off the light. And real quick, we'll just go through some examples. I have 3 problems I will go through. The first example is going to be consisting of, a binary number that has fractions. So it's going to be some number with some decimal value afterwards. And the next number is just a straight up binary number to base 10. And the last one is just a base 10 number to binary. And these all should be relatively easy to do. The first one might take a little bit to do. Okay guys, well, the first thing we should do when we're looking at this problem is we should break it up into different parts. So the first part I'm going to be doing is just this left part that's to the left of the decimal. And let's look at this. So everything that we want to add from this number are the values that are 1. All the other like the zeros and all that, like you're not going to add them, because if you evaluate them, it's just going to come out to 0. So the only ones that you care about are the ones that have the 1 in them. So if we look here, we can just like outline it real quick. I'll write it out. So we have 2 to the 0 plus 2 to the 1 plus 2 to the 5. And this is also it's going to be 2 to the 0 plus 2 to the 6. So this should equal 1 plus Um, oh, and I'm sorry, this isn't 2 to the 6, sorry. Oops. Okay, this is, everything's still the same. Sorry, I don't know why I added those right now. Okay, so 2 to the 0 is 1, so we have 1 plus 2, and then 2 to the 6, you know, if you can't do 2 to the 6 in your head, let's say for example, 2 to the 3, 2 to the 3 is 8, and then if you do another 2 to the 3, or if you multiply it by 2 to the 3, then that's going to give you 2 to the 6, so it's going to be 8 times 8, oh, I'm sorry, not 8 times 8, it's going to, alright, I'm sorry, I keep writing the wrong numbers down, I don't know what's wrong with me. Okay, so we have 2 to the 5, this is why I'm getting confused. Okay, so let's say we know 2 to the 3, 2 to the 3 would be 8, and then to get 2 to the 5, you just need to multiply that by 2 to the second, which will be 4, so it's going to be 8 times 4, which is 32. So this should equal 35, base 10. Okay, so just gotta keep this in mind, and then now we're gonna look at the right part of the decimal. Okay, so just write down everything, that has a 1. So we're gonna have a 1 over 2 to the 1 plus 1 over 2 to the 3 plus 1 over 2 to the 4. Okay, so if we, evaluate this out, 1 over 2 to the 1 is 1/2. I mean, you can write this however you want. If you're comfortable with just fractions, and write that. So it's 0.5, and then 1 over 2 to the 3, which is 1 over 8. So that's going to be 0.125. And then 1 over 2 to the 4 is 16, and that's going to be 0.0625. And if you write out this result, and you add everything together, you should get 0.6875, and this is base 10. Okay, so now we just combine everything together. What you got on the left of the decimal, we'll write that up. So we got 35, and then we'll write everything to the right of the decimal. And everything to the right was this this 0.6875, and this should be our result. I'll go ahead and underline it with a different color, and don't forget base 10. So the number that this binary number represents the decimal number 35.6875. Okay, well, let's take a look at this example. Okay, so the same steps apply here. Everywhere where you see a 1, just take the power of 2 that corresponds to that placeholder and just add them together. So we'll just start from right to left, so that way we don't mess up. So in this example, we're going to have 2 to the 0 plus 2 to the 2 plus 2 to the 3, and then plus 2 to the 5. Okay, and then if we actually evaluate this, it's going to be 1 plus 4 plus 8, and then we have 32. Okay, so if you solve this out, 4 plus 8, that's 12, plus 1, 13. 13 plus 32 is 45. So this decimal number should represent 45 base 10. And if you want, you can reconvert this back to binary and check to make sure that you have the same result, but let's just continue on for now. Alright, let's convert 73 to base 10. So the steps that I told in previous videos was that, try to find the highest power of 2 without exceeding, this value right here. Okay, so if we keep that in mind, you can probably work this out once you figure out the powers of 2 for yourself. But, the highest power that we can go up to without exceeding 73 is actually 2 to the 6th. So we're going to take this number, 73, and then we're going to subtract it by the value that corresponds to 2 to the 6th. And 2 to the 6th is equal to 64. So 73 minus 64, that is 11, I believe. Actually, no, it's not 11. It's actually 9. I apologize, guys. We need to be a little more careful here. Okay, so then we have 9. And then now we do the same thing, we do 9, and then the highest number that we can get to without exceeding 9 is 2 to the 3. So that's going to be 9, 9 minus 8. I'll just write it out. 9 minus 8, which is equal to 1. And, we do the same thing for 1. So a value that we can take without exceeding 1, would be 2 to the 0. So 1 minus 1 is 0. Okay, so once we, evaluate this, we just take these placeholder values, and that's where we stick our 1 at. So let's just start from the right since it's going to be easier. So we put a 1 where 2 to the 0 is at. 2 to the 1 is 0, 2 to the 2 is 0, 2 to the 3 should be a 1, 2 to the 4 is 0, 2 to the 5 is 0, and then 2 to the 6 should be a 1. So this decimal number, the binary equivalent for that number is, the result that we got here. So just underline it. And I guess that's it for now. Hopefully this video recap maybe helps you out a little bit. I know some of the examples that I worked out in the previous videos are pretty simplistic, and hopefully in this one it helps you understand a little bit more. Also, just to make note of this, because you might see this sometime in the future, everything that we've been dealing with so far is what's known as unsigned binary, which pretty much just means that, its values from, 0, to like whatever, however big you want to represent it. So it's like could be 0, let's say we're dealing with an 8-bit number system, then it'd be like 0 to, 255. So it's pretty much, non-negative numbers. And then a signed binary represents negative numbers. So it's anything from like -1 to, and if we're dealing with 8 bits, then it'd be -1 to whatever. 8 bits was just whatever. It's just an example, but I'm pretty sure it's actually -128. But unsigned is pretty much 0 up, and then signed represents negative numbers from -1, down to -infinity. So you might come across this if you're taking any, let's say like digital systems or like some kind of circuits class or something, or computer architecture class where you deal with like hardware and stuff, or memory and stuff. So right now we've been just dealing with unsigned, and in future videos I'll probably go over signed binary, but there's other concepts that we need to cover before I can get to that point, and hopefully this video helps I know it's supposed to be a quick recap, but you know, sometimes these videos take a little longer than expected. I kind of just sit down and record them. I'm not really planning out a whole bunch of stuff, but hopefully in the future videos I can make these videos a little bit shorter. But for now, take care, and until next time.